So why did we even learn how to find determinants yesterday? Again, pretty much everything we learn with matrices is just other ways to solve systems of equations. So today we're going to use Cramer's rule. And I actually really like Cramer's rule. It's pretty cool. So the solution of a linear system can sometimes be expressed using determinants. To illustrate, we're going to solve this system right here. Okay, so I'm going to solve with elimination, so I'm going to multiply this equation by d. I'm going to get rid of the y's first, and then multiply this equation by negative b, so that when I add them, they will be the y's, that will eliminate the y variable. Okay, so this is what I get, and now I'm going to add these two equations, and I'll get ADX minus BCX. These eliminate to 0, equals RD minus BS. We're going to solve for x, so factor that out. Then we divide on both sides, and x is equal to RD minus BS over AD minus BC. I'm not going to show you the whole proof, but you can also get y in the same way. Y is equal to AS minus CR over the same thing, AD minus BC. Recall that the determinant of a 2 by 2 matrix in the form ABCD is AD minus BC, and so the numerator and the denominators of x and y can actually be written as determinants of 2 by 2 matrices. So let me show you first with x. X is equal to RD minus BS. Okay, so that means we take the determinant of, usually it's A, B, C, D. R is multiplied by the diagonal D, minus B is next, and then the last letter is here. Okay, divided by, this is also, the denominator is also a determinant of a 2 by 2 matrix, literally the one in the formula, AD minus BC. So A, B, C, D. And similarly, we get y is equal to, okay, ARCS over determinant A, B, C, D. Some of you may wonder why I have the R and the C in different place than you thought it would go, but it doesn't actually matter if you have C here and then R there, or R here and then C there. You're going to get the determinants of those are equivalent. So for our purposes, we're going to follow this pattern to show something specific. For y's, the RS is in the y column. For x's, to find x, the RS is in the x column. So let's take a look at that. Cramer's rule for a system, for systems in two variables. As you can see, the RS, I hope that's not a good color for this. RS are the constants, whatever the equations are equal to. For the x variable, RS will replace the x values. So instead of, our coefficient matrix is A, B, C, D, our variable matrix is XY, and our constant matrix is RS. So when you get, when you find x, then RS will replace the x values in the original matrix, and when you're trying to find y, R and S will replace the y values in your original matrix. Again, everything is over the determinant of that coefficient matrix. So this matrix right here, the determinant of that is the denominator of any variables. And because that's a denominator, it cannot equal 0. In simpler notation, we write that D is the coefficient matrix, D of x is the replacement of x, D of y is the replacement of y's, so that we get, this make the most sense to me and was the easiest to remember, that x is equal to the determinant of the x matrix, the one where you replace the x's, and y's is equal to the one where you replace the y's, both of them dividing the determinant of the coefficient matrix. Woo! Okay, it sounds complicated, but it's actually pretty cool and not too hard, especially if you watched my last video on how to find determinants. If you don't know how to find determinants, you're going to be super lost. Let's use Cramer's rule to solve this system of equations. First, I'm going to write the coefficient matrix, and then, of course, just highlight R and S for our replacement purposes. Remember, the coefficient matrix is called D, so first we're going to find the determinant of D, the determinant of dx, the determinant of dy. So the determinant of D is 16 minus 6, so that would be 10. D sub x is the matrix. Negative 1, 2 is the first column, so your R and S replace the x's for D of x, D sub x, and then your y's remain 6 and 8, the coefficients of your y's. So now we'll find the determinant of D sub x. That would be negative 8 minus 12 equals negative 20. D sub y is the matrix that contains the coefficients of the x values, but instead of the coefficients of the y's, has the constants. Go ahead and find the determinant of that matrix for plus 1. Okay, so to find x, to actually solve for x, we take the determinant of the x matrix over the determinant of the coefficient matrix. So we have negative 20 over 10. That's negative 2. And y is equal to the determinant of y matrix over the determinant of the coefficient matrix, which is 5 over 10. Okay, so the solution is negative 2, 1/2. And that's how you can use determinants and Cramer's rule to solve a system. Let's do one more example. Okay, so our coefficient matrix is 2, negative 3, 4, 1, 0, 6, 3, negative 2, 0. And we'll just highlight our constants. Those will be what replaces the variables. Dropping my stuff here. Okay, so this is matrix D, and we're going to find the determinant of matrix D. Okay, that means we have to expand upon a row or a column like we did in yesterday's lesson. And since we did it yesterday, I'm not going to bore you. If you don't remember the steps, I will have them shown here in a second. And we get negative 38. All right, we're going to do the determinant of the x matrix. So we're going to replace all the x coefficients instead of 2, 1, 3 as your first column with the constants 1, 0, 5, and the rest of the coefficient matrix will look the same. When you find the determinant, the easiest thing is to expand upon a row with many zeros, and I'll do that now. Okay, so I chose to expand upon the second row, so I only had to multiply 6, and of course the negative from the signs for our cofactors. Continuing on, the d sub y, determinant, that matrix replaces all the y coefficients with 1, 0, 5. This is what that looks like. And to find the determinant, I'm going to use the second row again, even though there's only 1 0 there. That's the most. Alright, so the determinant of the y matrix is negative 22. Continuing on to the z matrix. Where we replace all of the z coefficients with the constants 1, 0, 5. Here's what that looks like, and to find the determinant, I'm going to expand the second row because that has 2 zeros in it, and I'll go ahead and do that now. And that is 13. Okay, so I have summarized over here. I have summarized our findings, and so the x variable is equal to the determinant of the x matrix over the determinant of the coefficient matrix, which is equal to negative 78 over negative 38 equals 39 over 19. Okay, so that's our first one, 39 over 19. Similarly, we can find y and z. Using Cramer's rule, we have our x value, our y value, x value, y value, and our z value from that system of equations. Go ahead and write it as a point. Wow. These are some crazy looking fractions. Don't you wish you had done elementary row operations and put it into row echelon form? Even though finding the determinant of a 3 by 3 matrix over and over is a little bit tedious, wow. The solution to this system would have been so difficult with either elimination or Gaussian elimination or Gauss-Jordan elimination. So Cramer's rule really did come through for us. Have a good day.